The control of the ever-increasing number of high-speed jet and other aircraft demands a means for the rapid acquisition and display of accurate, continuous information on aircraft positions and identity. The control of air traffic originates from the ground, and radar is one of the aids used in air traffic control to provide the necessary services. As you know, primary radar emits short, powerful pulses, parts of which, upon being reflected by an object, in this case an aircraft, return to the radar antenna and appear as a small blip on the radar display, thus giving an indication of this aircraft's position. However, today's air traffic control requirements demand more, much more, than the position of an aircraft. It must be provided also with means for the immediate and positive identification of an aircraft. Secondary surveillance radar provides this means. It can identify and monitor even a very small aircraft at long range and at great height, provided the latter is equipped with a transponder. Briefly put, secondary radar interrogates, that is, it questions the radar transponder in an aircraft on the radio frequency of 1,030 megacycles. This interrogatory signal triggers a reply from the transponder in the form of a new and greatly strengthened signal on the radio frequency of 1,090 megacycles to the ground equipment, where it appears on the radar display in a distinct form. Now, let us look at some of the components which make up a secondary radar system. This building houses the interrogator, transmitter and receiver units, the deep routing equipment, the common and non-common decoders. We will discuss deep routing and decoding equipment later on again. The secondary radar antenna is what appears to be a bar mounted on top of the primary antenna. Both antennas scan the same area simultaneously and in synchronization. The components in the air traffic control center are the master control box and the associated sector remote control boxes. And, of course, the radar displays. Here are the airborne components in the cockpit of an aircraft: the receiver, signal processing and transmitter panel, and here the transponder antenna. We will now consider the operation of secondary radar in more detail. The simplest signal which might be used for interrogation is a single pulse. To avoid interrogation by haphazard or random pulses, transponders are designed to reply only to specified pairs of pulses. These are known as modes. It is the time interval between pulses of each pair which determines the various modes now available for use with secondary radar. Thus, a pulse spacing of 8 microseconds gives mode A, and a pulse spacing of 17 microseconds gives mode B. The replies from transponders triggered by modes A and B are used by air traffic control for identification and tracking of aircraft. A pulse spacing of 21 microseconds gives mode C. This has been designated for use in initiating automatic pressure-altitude transmission from aircraft. A spacing of 25 microseconds provides mode D. The use of mode D has not been decided. The air-to-ground replies are also combinations of pulses known as codes. At present, mode A is responded to by 64 discrete reply codes derived from 6 pulse designations. A1, A2, A4, B1, B2, B4. The addition of all the binary digits in the A group or B group totals 7, or the omission of all pulses from a group indicates a 0. However, secondary radar is capable of providing 4,096 discrete codes for reply to interrogation by each of the 4 modes, A, B, C, and D. Various combinations of 12 pulses make this possible. They consist of the 6 pulses in the A and B group we already know, plus 3 C and D pulses of equal value. Again, the sum of the binary digits of each group gives the code designation. For example, 4031. A special identification pulse, or SPI, can be transmitted with any code upon request by the air traffic controller, simply by the pilot pushing a button. The radar display then shows this aircraft as a specially reinforced blip. Certain codes have been adapted by ICAO for particular functions. These are the emergency code, 77. Should this code be activated by a pilot, the radar display looks like this, and a general alarm is given automatically. Code 76 is the radio communications failure code and looks like this. This is the general purpose code, 00. Now, let us look at secondary surveillance radar as seen on a television screen and under normal lighting. This is made possible by an electronic scan system capable of accepting primary as well as secondary radar information. It maintains a display of present as well as past information for as long as 120 seconds. Facilitating the analysis of complex situations and decision-making in the control of air traffic. And since it does not require the same degree of concentration when monitoring aircraft in comparison with a conventional radar display. In areas of heavy air traffic, a secondary radar display can be very cluttered with the replies of aircraft to other interrogators in the area, which of course are not synchronized with the display in question. This interference is called fruit. While decoding reduces this clutter, it is desirable to equip the decoders with a defruiting device, which accepts for decoding and display only replies synchronous with the interrogation, effectively removing this fruit. Transponder returns can be displayed either raw, coded, or decoded. This graphic shows the appearance of the raw video code train, 47. There are 4 separate divisions between the framing pulses and the information pulses, indicating that the reply is composed of A4 and all the B pulses. Here, code 77. It gives all the pulses of the A and B group between the framing pulses. Obviously, it is difficult and undesirable for the controller to try to distinguish visually the individual code trains on his display, especially when this is not defruited. The remote control box enables the controller to defruit and decode transponder returns, so they will appear on his display with a maximum of 2 slashes. You will observe these throughout this film. A radar controller must know when to expect interference. Fades and false targets. And radar jamming. And cope with these situations when they occur. Your instructors will explain these phenomena in greater detail. Aircraft attitude will affect SSR quality of display. Since the transponder normally is located at the bottom of the aircraft, a turn or steep climb may block the pulse pairs transmitted by the interrogator, and the transponder will not reply. However, in most instances, good primary radar returns may still be observed. A transponder return from an aircraft which is close to the antenna sometimes will be displayed as a ring around instead of as a distinct target on a definite azimuth. This may be corrected by requesting the pilot to squawk normal. That is, turn the control of the transponder to the normal position or turn the transponder off entirely by instructing him to stop squawk. But side lobe suppression systems remove this ring around more effectively. The SSR interrogator antenna radiates the vast majority of its energy within its main beam width. Some energy is radiated in other directions throughout 360 degrees of azimuth. It is known as side lobes. Since the airborne transponder must only be triggered by the pulses in the main beam and not by these side lobes, arrangements are made for an omnidirectional control pattern to be also transmitted by the ground interrogator. The design of the airborne transponder is such that it will only reply when the interrogation is more powerful than the omniradiation field. And this is only the case within the main beam of the SSR interrogator antenna. This technique is termed side lobe suppression, SLS. Distances measured by radar are slant distances. That is, the distance along a straight line from the ground station antenna to to the aircraft, and not the horizontal distance to the point on the ground directly below the aircraft. The position indicated on the radar display is therefore only an approximate geographical position. The height of the aircraft above the antenna is also important. Since the distance measured is the slant distance, the display cannot show a distance which is less than the vertical distance from the ground to the aircraft. The radar blip of an aircraft flying at flight level 270 over a ground station located at sea level, for example, cannot be displayed at less than 5 miles from the antenna site depicted on the radar display. When the slant distance is greater than the height of the aircraft above the ground, the inaccuracy introduced is not too important, because it affects all aircraft flying in the same area at approximately the same flight levels to the same extent. However, radar separation minima must be designed to allow for the inaccuracy. The principal advantages of secondary radar to air traffic control are reinforcement of the primary radar blips, which make it easier to monitor and track aircraft. The display of decoded radar responses provide initial and continuous identification of aircraft without the need for an aircraft to make identification turns, thus reducing the number of radar vectors. The ability to detect aircraft emergencies or communications failures immediately. It facilitates the provision of separation between aircraft. These factors reduce the overall communications workload between controllers and pilots considerably. It also improves the coordination of the various ATC units and individual controller positions. To identify an aircraft prior to accepting responsibility for control, a controller can request a pilot to change the transponder code. The controller will call a specific flight.
Pan American 807, this is Friendship Control. Squawk code 47 Alpha and ident.
The meaning of this phrase is select mode A and code 47 and use the SPI, the Special Position Identification Pulse. The pilot, after acknowledging this message, will set his transponder control as requested. The controller will receive immediate positive identification of this aircraft on his display. Normally, specific code assignments are made for climbing aircraft on departure. And a different code for those arriving and descending, greatly facilitating control of such traffic. Similarly, different codes may be assigned to aircraft cruising above a specified flight level and those flying below it. Thus, identification of aircraft under control is always available to the radar controller, and traffic can be monitored continuously with much greater ease. Today's secondary surveillance radar, with its great height and range capacity, already is of great value to the air traffic controller and pilot. But its full potential is much greater when all the modes and codes now available are put into full use with appropriate instrumentation. It will provide still better utilization of airspace, allow the automatic tracking of aircraft, give continuous aircraft position and automatic pressure altitude information, allow the automatic visual transfer of control, filter out aircraft not within the bands of flight levels under control, thus relieving the controller from many routine tasks. Indeed, the future of secondary surveillance radar assures still safer and more efficient air traffic control.